Hello everyone, in this video we're going to continue to discuss quadratic functions and completing the square, which we'll use for graphing quadratic functions via transformations, and we'll also use that technique of completing the square for solving quadratic equations by extracting square roots. Just a reminder, we started this in a previous recording, that this main idea for completing the square comes from multiplying out the standard binomial x plus a number. I had that number listed as t. We always end up with each individual term squared, but we end up with double the cross product. So x times t times x doubled. Alright, thinking about this in terms of the relationship between the coefficients that we have here, a coefficient of x, and the constant term that we have here, which is t squared, the relationship is what's being squared is half of what that coefficient is. So if you multiply 2t by 1/2, divide it by 2, you just have t, then squaring that would give us the constant term. How we are going to turn that around is if we come across an expression that has a quadratic expression, polynomial expression of degree 2, x squared plus a number times x, I'm calling that d for this discussion. D is some numerical coefficient, it could be positive or negative, fraction, integer, whatever. We do is we multiply it by 1/2, we divide it by 2, then we square that result, add it and subtract it into our expression, and we then can take use of this perfect square reversal. Alright, so if we can add that kind of appropriate expression in, what we're saying is the right side will equal the left side up above here. Alright, or if we're thinking about working this down in terms of our steps, these three terms, x squared plus dx plus d divided by 2 squared, will turn into one perfect square binomial expression. Okay, notice there's no just x squared versus the next term separately there. It's one expression involving x in parentheses all squared. Alright, we did some examples. We're going to do some more. I just wanted to mention there's a different way we could think about this previous identity, and I'll just kind of go through a quick derivation of that, because that's really how we're going to see this happening in these examples. So we start out with an expression like x plus a number times x squared plus a number times x. And again, d could be positive or negative. If d was negative, we would think about that as x squared minus something x. But all right, and then what we do is we take that expression, okay, and we're going to just add in d divided by 2 squared. Now we can't just do that, that'll change the value of the expression, so we then have to subtract it off also, which is like us adding in a convenient form of 0. Then what happens here is that these first three terms turn into a perfect square binomial. Those first three terms become, in parentheses, x plus d divided by 2 all squared. All right, so those first three terms go into that binomial being squared, and then we have this number that we're subtracting off also. So again, the key idea is that we're combining those x squared and x terms via this identity into that one binomial expression squared. It's going to have several uses for us, as we're going to find out. Okay, we're going to do a couple more examples of just getting used to completing the square, and then we'll do some graphing, likely also in this video. Alright, so the first example I want to do is here, x squared plus 6x plus 1. So just quick taking a note here that the number d for this example, the coefficient of x, is positive 6. Alright, so then what we want to do is we want to take that number, divide it by 2, cut it in half, and that gives us 3. So that's our special number that we're going to then add and subtract in to our expression. Okay, so this is then going to equal x squared plus 6x. Now this looks a little different than up above where I had x squared plus dx because we have that plus 1. So just kind of push that plus 1 off and to the right, and then what we're going to do is we're going to add 3 squared, and I'm just using parentheses for extra emphasis, and then we're not going to add it again, we're going to subtract it. And then we're going to kind of think about that these first three terms become our perfect square binomial. The other two terms, where numerical constants, we'll just leave in. So again, the x squared and the x term roll together into one binomial, x plus 3 being squared, in parentheses squared, and then we still have minus 3 squared, which is 9 plus 1. So our final answer then would be x plus 3 squared minus 8. Okay, so what we started with was x squared plus 6, x plus 1. What we're ending with is, again, looking a little bit differently. So it looks different. It's the same exact expression. If we plug a number in for x in the first expression or the second, we'll get the exact same results. Okay, and therefore we're going to have the same graph. All right, let's do a couple more of these. So next one, all right, again, let's just make a couple of quick notes here for this. The number d comes out negative here. We had to include the sign. We could think about that as x squared plus negative 8x. So d is negative, I'm skipping one step ahead here. D is negative 8. Dividing that by 2 would give us negative 8 divided by 2, which is negative 4. So that's the special number that we want to add and subtract in to our expression. Okay, so again, we're going to say that this is equal to x squared minus 8x. We're at the plus 2 last. Then we want to add, in parentheses, negative 4 squared, subtract negative 4 squared, and then we have that plus 2 hanging out at the end still. And once again, these first three terms are the important ones. That becomes the perfect square binomial. Now, we got to be a little careful with this one. It's x coming inside there, plus, I'm just going to do this for extra emphasis here. You can do that in one step. Plus negative 4, which we're going to write in the next step as x minus 4. That's all in parentheses, squared. Now we got to be a little careful with these next couple of terms. We're subtracting a number being squared. Whenever we square a number, it's got to come out positive. So a square negative number is going to come out to be positive. In this case, negative 4 squared is 16. These two negatives, I'm just going to put them in here for a second and then get rid of it. These negatives right here do not cancel. All right, you got to square first. Order of operations tells us to square first, then subtract, and then we still have the plus 2. Okay, so what's our final answer going to be here? We are going to have x, and then we can write as minus 4 on the inside, squared, and then negative 16 plus 2 is minus 14. Okay, so that's equal to our original expression. And again, it just looks different. It's going to have there's going to be certain benefits to us doing the completing the square process. Okay, let's do one more example with just completing the square, and then we're going to apply it to graphing quadratic functions after. In the next video, we will talk about solving quadratic equations via completing the square. All right, so one thing that I've repeated in a lot of our work is to not change our approach, not to change our game at all when the numbers get harder. So in this case, the numbers are getting a little harder because d is negative, that's one part of it, but it's also not divisible by 2. Okay, so what do we have to do here? We have to deal with the fractions. All right, so our life is a little harder here. The process is exactly the same. So d is negative 5 over 2, which we could think about as a decimal, negative 2.5, but I'm just going to leave it as the fraction. All right, so what are we going to do? Start out with our original expression. And then we're going to add in. All right, so we got our x squared term, we got our x squared, we're now going to add in, that's our special number over here, negative 5 over 2. That's what we're going to square and add that in, which we just did here, and then subtract it in. So again, we're really just adding in 0 by doing that, which doesn't change the value, it's just now going to change the way it looks when we factor the first three terms. So nothing's changed. We add in that number. This turns out this number doesn't simplify nicely like it did in the previous examples. So what do we get here? We still get x, in this case, plus negative 5 over 2, which I'm just going to write as minus 5 over 2 quantity squared. And now we've got to just deal with the fractions that we have left over. When we square the fraction negative 5 over 2, it comes out positive. We square the numerator and the denominator, we get 25 over 4. Plus 2, which let's think a step ahead here and write that as 2 over 1 to then find the common denominator, which is 4. So we're going to multiply the bottom and the top by 4. All right, and then that's going to give us our final result. We get x minus 5 over 2 quantity squared, and then we're going to have negative 25 plus 8, which is negative 17 over 4. All right, so the numbers got a little harder there. The process stayed exactly the same. All right, continuing on, we're going to shift gears a little bit. In our next example, we're going to use the same technique of completing the square, but we are going to use it to graph a quadratic function. So what we're going to do is convert it from what we would call a general format to vertex form. All right, vertex form is what we've just been pretty much accomplishing in the previous examples. All right, and it's going to allow us to graph the quadratic function easily as in terms of transformations of the standard graph y equals x squared. Okay, so we're supposed to complete the square to graph it, and then we also want to do this, state what the vertex of this parabola is. The graph of any quadratic function is a parabola, either opening upwards or downwards, and we want to state the range of the function. Alright, so our process is the same, and we might have done this example in a previous recording. So just quick note again, for the coefficient of x, it's 6. So dividing that by 2 gives us 6 over 2, which is 3. Okay, and now we're just going to go at it. Let's rewrite our function. So what do we have? We have x squared plus 6x, and then we're going to add, I think we did this example actually in this video, 3 squared, subtract 3 squared, and then plus 1. The first 3 terms, once again, are becoming the perfect square binomial. This is just an algebraic rewrite. Sometimes, though, rewriting expressions can be more difficult than solving equations. All right, and then we get minus 9 plus 1. Okay, so our final answer for this one is x plus 3, in terms of our completing the square portion of this, minus 8. Okay, and again, those x squared and the x terms are rolled into that binomial being squared. You can certainly just check this work by multiplying the binomial out, and you will see it's exactly equal to x squared plus 6x plus 1. All right, now what's the advantage of this vertex form? This is what we have at the end here. The advantage of the vertex form is that it allows us to think about this in terms of simple transformations of the original function y equals x squared. All right, because we know inside changes, we've learned this with our function transformations, we know how that affects the graph. Adding 3 on the inside shifts the graph left 3 units. All right, subtracting a number on the outside, remember the inside changes kind of do the reverse of what we think, but the outside changes do it in a more direct fashion. This is going to move the graph down 8 units. All right, so in terms of us just getting a simple sketch, that's very useful. All right, because now we can just very quickly, and not perfectly at all, sketch on our paper, shifting left 3 and down 8, put a point. That's where the vertex of the parabola is going to be, and then it's going to open up from there. Again, I'm not going to have a perfect sketch on this. Okay. I can do a little better than that, I think, though. Maybe I'll try this third time. But it's going to look something like that. Again, not a perfect sketch, so I'm just going to fudge it a little bit here. The parabola is looking a little bit more like a parabola, but there we go. All right, so now what are the coordinates at this point? Well, we went left 3 to negative 3, and we went down 8 to negative 8. So the coordinates of the vertex are negative 3, negative 8. Okay, and that also allows us to see what the range is. All right, so that's the coordinates of the vertex. We can also see the range on the y-axis. All right, where does the graph show up relative to the y-axis for this function? It shows up down to negative 8, but no lower than negative 8. So the range we would think about in terms of interval notation or inequality notation, saying that the y's are always greater than or equal to negative 8. If we want to express that in interval notation, we could do that by negative 8 to infinity. All right, let's do another example where we're graphing using the completing the square technique. All right, so the next example I want to do is going to illustrate something a little bit different, in that we can only apply the completing the square identity, which I'm going to write down up above here, x squared plus a number times x. Rewrite this again here. X squared plus a number d times x can be rewritten as x minus d over 2 quantity squared, and then minus the compensation term d squared over 2 d over 2 squared. We can only do that when the number in front of x squared is positive 1. All right, so we've only seen that when the coefficient in front of x squared is positive 1 that I wrote there in red. If the coefficient isn't positive 1, we have to force it to be positive 1. So for this example, it's going to show us something a little different. What we need to do is we need to divide out the negative from the first two terms, the x terms. So dividing it out from x squared, we're going to get positive x squared. Dividing it out from negative 4x is going to give us positive 4x. Then I'm going to leave myself a little bit of room inside that bracketed term, and then outside of that I'm going to put the plus 3. So let's just separate the constant term from the x terms here, but we've got to factor out this number. In this case, what we factored out is negative 1. All right, now what we're going to do is we're going to complete the square inside the bracket. So the coefficient of x is now positive 4. So dividing that by 2, we get 4 divided by 2, which is 2. So we're going to square that number and add and subtract that in. And I'll just do that right here. So we're going to square 2, add it in, and subtract it in. Okay, now the first three terms in the bracketed expression up here, so it's a little more complicated, this part of it, that's going to turn into the perfect square binomial again. And then we still have the negative 1 in the front. Those first three terms are going to become the perfect square binomial x plus 2 quantity squared. And then we still have minus 2 squared, which is 4 on the outside of that. And we can't forget our plus 3 at the end. So the completing the square process is a little tougher here. All right, but it's going to lead us to, again, another expression, quadratic expression, which we can think about as a graph of as transformations of the graph of y equals x squared. All right, now to finalize this, we're going to redistribute the negative 1 through. So now that we've completed the square, we've got the x terms rolled together into 1. We're now going to put the negative 1 back through the bracketed term, which is going to give us negative 1, or just negative in front of the x plus 2 squared. When we negate the negative 4, it becomes plus 4, and then we've got plus 3. All right, so finally, and this function's name was g of x, or g, what is the formula for g, or g of x? It is negative the quantity x plus 2 squared, and then plus 7. All right, now let's unpack that in terms of transformations of the graph of y equals x squared. So what do each of these things do? We see the squaring outside the parentheses. So inside of the x squared function, we have x plus 2. That tells us, again, to go left 2. What's new about this one is this minus sign. All right, if we look back at section 1 for unit 3, that negative on the outside of this function is going to reflect the graph over the x-axis. And then lastly, the 7, it's just going to shift it up 7. That part's a little easier. So reflecting the graph over the x-axis is now going to give us a upside down parabola. So let's once again just quick sketch it. It doesn't got to be a perfect sketch. All right, let's just give a quick sketch to this, maybe in stages. All right, so what we say, we're going to go left 2. So go left 2, draw your standard parabola. Then reflect the graph over the x-axis. That's going to go upside down now. Then take that result and shift that up by 7 units. And again, not a perfect sketch, but it's going to look something like this. Again, far from a perfect sketch. We can use Desmos to get a more accurate sketch for this, but we can certainly see what the vertex is. It's at negative 2, 7. And we can see what the range is. The range is, in this case, everything less than or equal to 7 for this problem, right? It's all y values less than or equal to 7. 7 is the highest point relative to the y-axis on this graph. So if we were going to express this in interval notation, it would be negative infinity up to 7 with the closed bracket on the 7. Okay, let's try to fit one more example into this video. This one I'm going to maybe go through a little quicker, but the numbers are going to not be that fun. So if you need to, pause the recording to go back and review this. Alright, so the variables in terms of t here, once again, we don't have the coefficient of the squared term being 1, so we need to factor that out. So in this case, we're going to factor out 2. That's going to leave us with t squared. We want the coefficient of the t squared to be 1. It does not leave us with a nice number, though. In front of t, we have 3 divided by 2. Because keep in mind that when we're factoring out 2, it's like multiplying and dividing by 2. So if we multiply by 2 in the front, we then have to divide each of those terms inside by 2. Well, 2t squared gives us t squared. The 3, though, we cannot, does not divide evenly by 2. All right, so we got to deal with it. Our number in this case, d, is negative 3 over 2. If I divide that by 2, what does that look like? We get negative 3 over 2 divided by 2. We know that when we multiply by or divide by a fraction, that changes it to multiplying by the reciprocal. So we got to multiply that by 1/2. So our special number to add in here is negative 3 over 4. So we're going to go back up top here, and we're going to add in negative 3 divided by 4 squared, and then subtract that right off so we don't change the value of the function. And then we're going to rewrite this. All right, so continuing on, it's 2 times the first 3 terms, not much to think about. It's t minus, in our case, 3/4. So again, not real fun numbers, but still process unchanged. So it's t minus 3/4 all squared. That's the first 3 terms. So those 3 terms that is underlined become t minus 3/4 squared. And then we're going to have minus, squaring the negative 3/4 is going to give us positive 9 over 16. Okay, fine. Now distribute the 2 back through the parentheses, through the bracketed term. What's that going to give us then as a final result? So our function, capital M of t, is really going to be 2 times t minus 3/4 all squared, and then minus 2 times 9/16. Well, 2 goes into 2 once, it goes into 18, or 16, pardon me, 8 times. So our final answer for this would be 2 times t minus 3/4 squared, and then it's going to be minus 9 over 8. So once again, quickly in terms of the transformations, what do we have going on here? This is now going to shift the graph. Okay, so this is going to shift the graph to the right this time by 3/4. The 2 on the outside, that's a vertical stretch by a factor of 2. All right, so that's going to pull those points that are not on the y-axis higher up by a factor of 2. And then this is going to shift us down negative 9 over 8. All right, so again, it doesn't come out very perfect for this in terms of nice numbers here for this one. I'll just give the quick sketch for it though. Again, right, we're going to go right 3/4. And then we're going to take our normal parabola, and then it's going to be a little bit skinnier. And then down negative 9 over 8. So the final graph is going to look something like this. Again, we could check this with Desmos. Again, not a perfect picture right there, but we can definitely say the vertex is at negative 3/4, or positive 3/4, and then negative 9 over 8. The range, let's just quick state that for the last thing to do. The range for this one would be negative 9 over 8 to infinity, all y's bigger than or equal to negative 9/8. And that's it for this video.